What's happening?
Hello, everyone. I'd like to start with a couple of announcements, but first, can someone confirm that I can be heard, please?
We can hear you.
I
Okay,
can hear
thank you.
you.
Thanks very much. I want to remind, first of all, people whose Penn State user ID starts with letters AR through CB, please try to ask a good question today in the chat in order to get yourself and your fellow students extra credit. Also, as I mentioned last time, there will be some special question and answer session office hours today in advance of the quiz. They will be from 2:30 to 3:30 and from 5 to 6. And if you go on Canvas to the office hours page, you can get the Zoom info there. The rest of these announcements are the same as last time, giving some more details on the optional mastering physics-based extra credit, the remaining homeworks, and the content of the quiz and the final. You can find the content of the quiz on Canvas, and likewise for the final that will eventually appear there as well. So today we're going to continue our discussion of the Schrodinger wave equation and talk about how to solve the equation and then discuss some of the ramifications of that. And in particular, can quantum mechanics violate conservation of energy? So just to remind you, with the classical wave equation that we looked at last time, we were able to show that for a traveling wave solution, something that had sine of kx minus omega t in it, we ended up showing that the solutions told us that omega was equal to kc, which is just what you would expect for a massless particle, namely the photon, which is indeed the particle that we know carries electromagnetic waves. So this classical wave equation works for electromagnetic waves, but we know that if we want a wave equation for massive particles, we're going to have something that looks a little bit different from omega equals kc. And in particular, we want something that looks a little bit more like this, because we know that the particle has kinetic energy, and a particle can also be moving in a potential, like a gravitational potential, or if it's a charged particle in an electric field, and so on. So we want the wave equation to give us something that looks something more like this for a traveling wave than this, because our particles that we're going to deal with are not photons, and in general will have non-zero mass. So we want the wave functions that solve this new wave equation to have the general form that looks like what we're familiar with, some sine or cosine of omega t minus kx. That way we have a traveling wave. And for this to happen, the new particle wave equation is going to have to satisfy a few conditions. In particular, it's going to need to have a first derivative in time, so that we only pull out one value of omega when we take the derivative of solutions that look like cosine and sine of omega t minus kx. We're going to need a second derivative in space with respect to x, so that we bring down a k squared. So if you take a derivative of cosine omega t minus kx once, you bring out, with respect to x, you bring out one value of k. You take another derivative, you bring out another value of k, and you get the k squared. We also need the wave equation to involve the potential energy, because that appears in general for if you write down what the total energy is for a massive particle, it will have a term that depends on the potential energy. And finally, we also require that the wave equation is linear, because that's going to allow waves to do things like interfere, which we know that they do. So with all this in mind, Schrödinger proposed or postulated the following wave equation for massive particles, which has a second derivative with space. It has a term that depends on potential energy, and a first derivative with respect to time. And there's some other factors here, notably, for example, an imaginary number I. But let's see if this works for some specific cases. So the case we're going to deal with is a harmonic wave function for a free particle. So what's familiar is probably, this first piece, a cosine kx minus omega t. That is a traveling wave moving in the x direction. And this is just a generalization of that using complex numbers. And remember that complex numbers are mainly sort of a convenience. Ultimately, there is no physical reality attached to something that's imaginary. What we end up doing typically is using the imaginary numbers as a way to make it easier to write things down. And in particular, you can see here that, the big long expression there can be written much more compactly like that, using complex numbers. And ultimately, when we want to get a physical quantity or something that's physically real out of an expression involving imaginary numbers, we either just take the real part of that expression or we square it. And by square it here, I mean multiply by a complex conjugate. And that's something that you can imagine doing quite readily with the wave function, because again, the physical quantity that we get out of wave functions is from the square of that wave function, because that's what gives us the probability of finding a particle somewhere. Okay, so that was a rather long-winded introduction, but what I'm going to do now is take this expression for psi of x and t and plug it into the Schrodinger wave equation and hopefully get out something that looks like this up here. H bar omega equals h bar squared k squared over 2m plus potential. So if we do that, the first derivative of this wave function, psi of xt equals a e to the I kx minus omega t, gives you a minus I omega times psi. And the second derivative with respect to x gives you minus k squared times psi. And if you take these two things and plug them back in to the wave equation, so putting in the minus k squared psi at the beginning there and minus I omega psi over here, then multiplying everything out, you will get this as being what the Schrodinger equation simplifies to if you use a traveling wave for the wave function psi. And this is exactly what we wanted. We wanted this wave equation to tell us that for a massive particle traveling freely, it has total energy, h bar omega, equal to its kinetic energy plus its potential energy. Okay. That said, this is a very, very simple case, a free traveling wave looking like this. What's really powerful about the Schrodinger wave equation is that it works for basically all circumstances, including substantially more complicated ones than a simple particle moving freely with no potential. We'll do some slightly more complicated examples today and probably also on Tuesday, where there is some finite potential that the particle is moving in. And we'll see that the solutions to that agree with what we postulated before, using sort of ad hoc assumptions about de Broglie wavelengths and standing waves and so on. It all comes out pretty naturally with the Schrodinger wave equation. Now I want to point out that just like with Newton's laws, and in particular the F equals ma equation, Schrodinger's equation just came out of thin air. It can't be derived from anything, just like F equals ma can't be derived from anything. We can justify it with some, or motivate it by arguments like we just did, but there's no underlying equation from which Schrodinger equation comes from, just like there's no underlying equation from which F equals ma comes from. So in that sense, it really is a fundamental equation in physics. F equals ma is fundamental for Newtonian classical mechanics, and the Schrodinger wave equation is fundamental for quantum mechanics, and in particular cases where massive particles need to be treated not just as particles, but also as waves. In order to simplify things a little bit, what we're going to do is consider just what are called stationary states. And by this, we mean we're going to consider possible solutions that don't depend on time. Just makes it a lot easier. And the way to do that without going into great detail is you assume that the wave function can be written separably in a part that depends on x and a part that depends on time. And then if you put that into the Schrodinger equation here, you can get it to simplify to what's shown at the lower right, which does not depend on time and only depends on the position. And it's a little bit simpler. It's not a huge amount simpler, but it's much easier to work with than one that depends also on time. So we're going to focus on this equation from now on. So how do we solve such an equation? It's a second order differential equation. So there are general mathematical techniques for solving second order differential equations. You could also use computational techniques. The preferred method that we're going to use is to guess what the solution is. And the reason guessing works is because there's a mathematical theorem that says there are unique solutions to any differential equation. If you guess what that solution is, you're done. You have the solution. Also, in general, second order differential equations have two independent solutions. We write those here as psi1 and psi2. So the most general solution is going to be a linear combination of those two solutions. So we're going to start out with the familiar particle in a box, where we have a massive particle inside a container with perfectly rigid walls on either side. And it's got some kinetic energy due to its velocity. And it's only allowed to move horizontally in one dimension, just to keep things simple. One way to draw this is as sort of an energy diagram, where energy, the potential energy, is drawn on the x-axis here. And you see that in the region between 0 and L, the potential is 0. So that's the potential inside the box. And outside that region, shown in sort of an orange reddish color here, shaded, for x less than 0 and x greater than L, the potential is considered to be infinite, because these are perfectly rigid ends of the box. There's no way the particle can get through there. It's forbidden from getting in there. So this is the classically forbidden region. So we set the potential there equal to infinity. The particle itself, its energy, its total energy, which is the sum of kinetic and potential energy, is given by this horizontal line. So it has kinetic energy, in between 0 and L, it has some kinetic energy, and that makes up its entire energy, because the potential energy inside the box is 0. So what we're going to do now is try to answer the following questions using the Schrodinger wave equation. So first, what are the allowed energies? And what we're going to find is that the quantization of energies comes out naturally from the Schrodinger wave equation. And we're going to show that those allowed energies are quantized in exactly the same way as they were when we made the ad hoc assumption that the de Broglie wavelengths have to fit inside this box as standing waves. And remember, when we did that, we ended up getting that the energy levels were quantized. We're going to get the exact same answer by using the Schrodinger wave equation with this potential. We're going to get some additional information, though, from the Schrodinger wave equation. Namely, we're going to get the wave functions that are associated with each of those energy levels. And from those, we'll be able to determine, for any given energy level, where is the particle most likely to be. And we can determine that by just squaring the wave function and looking at what its shape is. So let's proceed. So the first thing we need to do is to determine what the potential energy function actually is. I mean, we drew a sketch of it over here, but let's write it down mathematically. And it's fairly straightforward. It looks like this. So the potential is 0 in between 0 and L, and it's infinite at x less than 0 and x greater than L, because the particle can't go outside of the box. So under those circumstances, what we will write is that psi of x must be 0 when x is less than 0 or x is greater than L. Why is that the case? What does that, what would happen, first of all, if this particle were to get to some position x greater than L? Someone put the answer if they think they know it. And yes, it would have an infinite potential energy there, infinite energy, in fact. And when that happens, you no longer have a physical situation. You can't have a particle with infinite energy. Not only is it violate energy, but infinite energy, it has no meaning. So by setting psi of x equals 0, what do we force to be the case? What does that tell you about the probability of the particle appearing at x less than 0 or x greater than 0? What will that probability be if the wave function is equal to 0 there? Right. So it'll also be 0, because remember, the probability of finding the particle there is the square of the wave function. If the wave function is 0, the square of 0 is 0. And so this means that the particle will not be in the regions x less than 0 or x greater than L. So there's no particle there. Good. The other thing that we're going to require is that right at x equals 0, right here, and right at x equals L, we want psi of x to also equal 0. And the reason for this is a little more subtle. The reason for this is you want the wave function to be smooth and continuous. And since we are requiring the wave function to be 0 to the left of x equals 0 and to the right of x equals L, we're going to require that it also equals 0 right at x equals 0 and right at x equals L. And then inside the box, in between 0 and L, it can have some finite value, some non-zero value. But this way it'll be nice and smooth and continuous, which is advantageous physically because you do not expect there to be discontinuities in the probability of finding a particle somewhere. So we want this wave function to be smoothly connected to 0 at the edges at x equals 0 and x equals L. Okay, so with those conditions, let's look at the Schrodinger wave equation and see what it simplifies to. And here we're just going to mainly use the fact that u of x is equal to 0 in between 0 and L. So if we do that, we can rewrite the Schrodinger wave equation just setting u of x equal to 0 like this. And then we can rewrite that without changing anything, just making a new variable basically, just so we don't have to carry around quite so many variables, and define this new variable beta squared as 2me over h bar squared. So that way we can just replace this 2me over h bar squared with beta squared over here. Just makes it easier to carry around variables. So here's our differential equation. The second derivative of psi of x with respect to x squared equals minus beta squared times psi of x. We can guess the solution to that equation. It looks like this. And the reason that works is because when you take the derivative of the sine of x twice, you get back the sine of x with a minus sign. If you take the derivative twice of sine of beta times x, each of those two derivatives brings out a factor of beta, so you're going to have a beta squared. You have that minus sign coming out. You will have basically the same wave function again after you've taken two derivatives with respect to x, but with a beta squared and a minus sign out in front. If you don't believe me, you should take this psi of x and plug it into this equation, take the second derivative, and you'll see that it equals minus beta squared times psi of x. Okay, so this is the general solution, general wave equation. Let's now see what happens when we apply what are called boundary conditions. In other words, the conditions of the problem that the wave function and the particle that it describes have to obey. So one of those conditions is that psi of x is equal to 0 is equal to 0. So at x equals 0, we require that the wave function itself be equal to 0. So we plug in 0 for x, here and here. And what that tells us is, well, this expression is just 0. Sine of 0 is 0. So it doesn't tell us anything about what the constant a might be. But it leaves here b times 1, because cosine of 0 is 1, equals 0. So therefore, b must be 0. So we've already dramatically simplified the wave function. So the general wave function, look like this, but now we know that that second part is going to be 0 in order to satisfy the boundary conditions. And then if we look at x equals L, where we also require that the wave function be equal to 0, we can ignore this because we know b is 0. We now know that a sine beta L has to be equal to 0 at x equals L, which requires that beta L be equal to an integer multiple of pi. So this is where the quantization shows up. Because remember that beta is related to the energy. Beta is just this new variable we invented in order to save ourselves from writing too much down. But it depends on energy. And so we see from this expression that the energy is going to depend on this integer n. Okay, we'll get back to that in a minute. Someone has just asked a question. How do we know that a isn't equal to 0? If you set a equal to 0 and b is also equal to 0, then what you have is that psi is equal to 0 basically everywhere, right? Because we know psi is equal to 0 at x less than 0 and at x greater than L. If we also set it equal to 0 inside the box, then that means that there's no particle, because psi squared is 0 also everywhere, and that's the probability of finding the particle. That means there's no particle. So while it is a solution, having a equals 0, it's a trivial solution, and it doesn't tell us anything about the particle, because in fact, by setting psi equals 0 to everywhere, you have stated there is no particle. So not only does a have to be non-zero, but we also have to insist that n starts at 1 and not at 0, because if n equals 0, we have the same problem. If n equals 0, then the wave function everywhere will be 0. And so the n equals 0 solution is actually the case where there's no particle. So n starts at 1, and we can write down the wave functions. They look like this. So there's this constant a that's still there. I'll show you how to find out what a actually is in a minute, times the sine of n pi x over L. And n here can be 1, 2, 3, etc. When n is equal to 1, we have the wave function for the ground state, where the energy is the lowest. And then for n equals 2, we have a different wave function, and so on. The allowed energies can be found by just setting the beta equal to n pi over L and writing out the actual value of beta, which is the square root of 2me over h bar, and then solving for the energy. And you see that the energy depends on n squared and some constants, h squared over 8ml squared. This looks exactly like what we got before, when we said that the Broglie wavelength has to be a standing wave inside of this box. Now we're getting it from a more fundamental equation, the Schrodinger equation, in exactly the same form. Not only are we seeing here that this energy is quantized, we're also seeing that because for any non-trivial set of solutions, n, the variable n, can only be a minimum of 1. It can't be equal to 0 because n equals 0 is a trivial solution. So n equals 1 is the smallest non-trivial solution. And if you put n equals 1 in here for the energy, you get a small non-zero value for the energy. So the lowest energy state is not 0. Remember, this is what's called 0-point energy, somewhat misleadingly, but it basically means that the lowest energy that a particle can have, if it's confined to a small region, is finite. It's not 0. Okay, so all this, remember, has popped out of this equation. So before, we basically only got this. We only got that the energy levels were quantized. Now, not only do we get that, we also got that the minimum energy is non-zero. And we are now also getting the wave functions associated with each of these energy levels. So for every value of n you use here, there is a wave function with the same value of n that can be assigned to it. But in order to fully write down what these wave functions are, we need to figure out what this constant a is. And so to do that, we use the normalization idea that we've talked about before, namely that the probability of finding the particle somewhere on the x-axis is equal to 1. Now in this case, the integral of psi squared dx, remember psi squared is the linear probability density, so we multiply it by dx to get a probability. And instead of going from minus infinity to infinity, we just go from 0 to L, because we know the particle is not going to exist at less than 0 and greater than L. And then we put in the wave functions, and I put a little subscript here on the A, a little n subscript, because I don't know if it's going to depend on n or not. But if you do this integral, you find that it actually doesn't depend on n, and it equals square root of 2 over L. So now we have the complete wave functions. We can write everything down. Looks like this. So here are the wave functions, or here's what the wave function is. For all values of n, for all energy levels inside this infinite potential well, they depend on n, where n is equal to 1, 2, 3, etc. It's an integer. And it equals 0 outside of this box. So it equals 0 when x is less than 0 or x is greater than L. We can also write down what the probability is of finding the particle at any particular place, and that's just the square of this wave function, which is given by 2 over L times sine squared of n pi x over L. We can plot these wave functions and their squares, and that's done over here, for different values of n. So for n equals 1, the wave function is shown in red, and its square, which is the physically meaningful quantity, is shown in green just below it. And here's the maximum probability point. You are most likely to find this particle right in the middle if it has this energy, the energy associated with the n equals 1, with the energy associated with n equals 1. If the energy is at the next higher level, n equals 2, then the particle is most likely to be found at L over 4 and 3L over 4, and so on. We can also show these wave functions at their various energy levels. So here is the wave function at energy level 1, and then energy level 2, which is just 4 times E1, because there's an n squared factor there, and E3 is at 9E1. And if we put in the actual values of all the constants that give the energy, so all of these variables here, H, M, and L, where L is 1 nanometer and the mass is the mass of the electron, then we get energies that are sort of comparable to the energies of electrons that are bound in an atom, just like before. Okay. So once again, re-emphasize that this expression that we got here for the energy is the same, exactly the same as what we obtained before using sort of an ad hoc approach with the Broglie wavelength and requiring standing waves. Okay, but now it came out naturally from the Schrodinger wave equation, applying suitable boundary conditions on the Schrodinger wave equation. And not only did we get the energies, but we also got the wave functions. And from the wave functions, we could find the probabilities of finding where the particle is. The wave function and the probabilities were not something that we could get using the earlier technique where we just used the de Broglie wavelength and standing waves. We only got the energy levels before. So I'd like you to consider the following question now. Let's focus on the n equals 2 energy level. So you see that here and here, as I mentioned before, at L over 4 and at 3L over 4, the probability of finding the particle is maximal. You're most likely to find the particle hovering around the L over 4 position or the 3L over 4 position. It can be over here or over here also, but it's most likely to be at L over 4 and 3L over 4. Conversely, there is zero probability of finding the particle right at 0 and right at L. So it can never get right next to the wall. And that's because, remember, it has continuity. It can never be less than 0 or greater than L, because there its potential would be infinitely large. So the final question is, all that I hope makes sense. The final question is, what's going on right here? So right there, there is zero probability that this electron can be found. You can make 1 billion measurements of this electron inside this box, and you will never find it at L over 2. So what does that mean? I'd like you to try to interpret that with this concept question. Okay, please get your answers in. All right. So most people voted for C. That's the correct answer. But it's a weird answer, if you think about it. So this says that the particle has some probability of being on the left-hand side, some probability of being on the right-hand side, but will never be in between. So the question is, how does it get from one side to the other? If it can be over at the left and over at the right, but never in between, that just makes no sense. So yeah, teleportation is one possibility. in the chat, I see. But the other possibility is if you look at the wave function up above in red, and imagine instead for a moment that instead of a wave function, that's a standing wave on a string. And sometime later, the string will be down here like this. And then sometime later, it'll be like that. And then a little while later, like this, etc. Okay, it goes back and forth like that. What's happening right there at the middle? Right in the middle there, we have what we call a node. And at that position, the string, in this case, is not moving, even though there's essentially a wave traveling back and forth through it all the time. Right there at that node, the string itself is not moving. So if we now come back and say, okay, this is now the wave function. Well, the wave function has a node right there. It doesn't change. It's not moving in a sense. And so it being 0 or its square being 0 as well, tells us that it's not appropriate to think of this as a particle, but it's more appropriate to think of it behaving like a wave in this case, where the wave has a node right in the middle. And while the particle interpretation says that there's a probability of finding the particle to the left and to the right, and there's 0 probability of finding it in the middle, thinking of this particle as also being a wave, I hope makes that a little bit more palatable. Because it sounds a little bit weird to say that the particle moves from one side of L over 2 to the other side without ever being in between. All right, I want to extend now our discussion of the Schrodinger wave equation from talking about potential wells that had infinitely high walls on either side at 0 and L to ones that have finite height walls on either side. These are more realistic for obvious reasons than infinite potential wells. You can't get infinite potential. You can have cases where there's a potential energy that's larger than the total energy of the particle that is confining it, without that potential energy being infinite, obviously. And this better models things like electrons and metals and so on. A classical analog is drawn here. So there's like this little soccer ball, and it's moving towards a barrier that it can roll up. If that soccer ball has an energy, kinetic energy, that's larger than mgh, the potential energy at the top of this barrier, then it will get through to the other side. Otherwise, it'll just bounce back and forth. So we can draw the energy of the particle to look something like this. Whoops. Something like this to make these equally sized, I should say. That's better. So here's the ball. And the ball actually has some energy. So we can say if it has some kinetic energy, that kinetic energy could be this value here. The potential energy up at the top, that's just mgh. And this kinetic energy, of course, is 1/2 mv squared. And it's also rotating, so it probably has 1/2 I omega squared as well. But let's just assume it's sliding around. If the kinetic energy is lower than the potential energy, then this ball will just sort of bounce back and forth like this, back and forth. And it will never escape. And it will never make it through this barrier or this barrier at all. Let's see what happens if instead of a soccer ball, we have a subatomic particle like an electron, and we ask what the Schrodinger wave equation predicts for this particle. So here's a drawing of what the potential looks like. So we're going to say that the potential is 0 inside the well, just like before. between 0 and L, the potential is 0, but outside the well, it's going to be some constant value, U naught, U sub 0. And the energy of the particle is going to be less than U sub 0. So this region, the two orange regions, are classically forbidden, because if the particle goes there, it doesn't have enough energy, I should say, to get there, because its kinetic energy is not larger than the potential energy in that region. So classically, it's not allowed to be there. But what about quantum mechanically? So now to solve the Schrodinger wave equation in that region, we need to keep the potential energy term around, because the potential energy, while it's 0 inside the well, is non-zero outside of it. So if we want to solve the Schrodinger equation in a region outside the well, so in this case, I'm going to focus on x greater than or equal to L, a similar argument holds less than or equal to 0, then we need to keep the potential energy around. So we have on one side d squared psi of x dx squared, and on the other we have 2m over h bar squared u naught minus e times psi of x. And to make things simple, we're going to write that stuff in front of the wave function as 1 over eta squared. So eta here is just equal to that quantity there. So there's nothing new there. It's just another variable that we're introducing in order to make it easier to write things down. So we have the following equation now. D squared psi of x dx squared equals 1 over eta squared psi of x. And I want you to contrast this with what we wrote down before, with the infinite potential well. So the finite potential well has positive 1 over n squared, sorry, 1 over eta squared in front of the psi of x. The infinite potential well had a negative beta squared in front of the psi of x. So we were able to guess a solution for the infinite potential well with sines and cosines. And now for the finite potential well in the region, in the classically forbidden region, we need to guess a solution to this expression, d squared psi of x dx squared equals positive 1 over eta squared psi of x. The solution exists for x greater than or equal to L. And in general, it's just this exponential, which you can verify by plugging that psi of x into this equation. And you'll see that, that it solves the equation correctly. If we apply a finiteness condition at x greater than or equal to L, which means that the wave function can't blow up to infinity as we go to large x, then that forces a to be equal to 0, and we're just left with this value for psi of x at x greater than or equal to L. And finally, if we apply a boundary matching condition at x equals L, just like we did before, we don't want any discontinuities in the wave function, then we write that psi of x at x greater than or equal to L is equal to psi edge, which is just some number, times e to the minus x minus L over eta. So let's see what this means. If we solve, in addition, for the Schrodinger wave equation at x less than or equal to 0, we will get something very similar to what I just wrote down here. And if we also solve for the region in between 0 and L, we'll get sines and cosines. So I'm just going to skip over all that and just show you what those look like. Here's what those wave functions now look like. So on the right is the infinite potential well case, the particle in a rigid box. And on the left is the finite potential well case for the particle in a box where the potential walls are not infinitely high. And what you see is that there's some finite probability that these wave functions will appear in the classically forbidden region. So that means that quantum mechanically, this particle is allowed to be in a place that violates conservation of energy. That's not true for the infinite potential well. There is no wave function. The wave function is identically zero in the orange region. Okay, so there are a couple of questions we need to ask and see if we can understand. How do these wave functions differ from one another, the finite and the infinite case? And how probable is it for the particle to actually be in that classically forbidden region? So let me first ask this question. Why do you think the energy levels in the finite potential well differ, and they're lower than the ones in the infinite potential well? So what I'm trying to say here is if you look at, say, the n equals 3 level, you can see that the energy for the infinite case is 0.848 for n equals 3, but it's 0.585 for the finite case. It might help answer this question if you look at the n equals 2 cases and compare them to one another. And I say that because there's one full wavelength here in between, in this case, 0 and 2. Okay, get your answers in, please. All right. So we have a variety of answers we're given. The correct answer, or the most correct answer, I should say, is A. The de Broglie wavelengths are longer, and you can see that again. If you look at the n equals 2 case, we have in the infinite potential well one full wavelength, whereas if you look at this region here in the finite potential well for the n equals 2 case, we don't quite fit in the full wavelength. So the wavelengths are longer in the infinite potential well. And remember that the wavelength, the de Broglie wavelength, is inversely proportional to the momentum. So if the wavelength is larger, momentum is smaller. If the momentum is smaller, then the energy is smaller. You could also argue for answer C being correct. There is now a finite probability to be at the walls, whereas in the infinite case, it's identically zero to be right at the wall. And by having a finite probability at the wall, the wave function would have to have been stretched out a bit. So that's also a reasonable answer. But the particle doesn't lose any energy in the orange regions. And even though right here, these wave functions look like they're overlapping as drawn, that's just because the energy scale is a little too compressed, but they're not actually interfering with one another. Okay, so finally, I just want to introduce the concept of what's called the penetration depth, eta. And we can talk about what is the probability for the particle to make it or to be found in that region, let's say x greater than or equal to L and a little bit beyond it. So let's think of the case where the particle is 10 etas, where eta is a measure of distance from the edge. And what's the relative probability of it being there versus being right at the edge? So if you write down what the probability is, or sorry, what the wave function is, right at the edge by plugging in x equals L, you get that it's just size of edge, where that's some number. If you plug in x equals L plus 10 times eta, then you get that psi edge times e to the minus 10. And the relative probabilities involve squaring these two wave functions and taking their ratios. And you see you get 2 times 10 to the minus 9. So there's a very low probability that you'll find the particle in this classically forbidden region. And when you do find it there, it'll only be there for a very short amount of time. So We are going to apply this to the idea of quantum mechanical tunneling. In the classical case, this ball will never get over that barrier. But if instead of thinking of a barrier for the Schrodinger wave equation, a well for the Schrodinger wave equation, we think of a barrier like this. That's this picture down here. We can ask, what's the probability that a particle on one side of that barrier, without sufficient energy to just jump over the barrier, can it go through the barrier and appear on the other side? And the answer is yes, and we'll discuss how that can happen. And we'll also talk about next time scanning tunneling microscopy, which is a technique that relies on quantum mechanical tunneling to work. Okay, thank you very much. And I remind you that later on today, there will be some special pre-quiz 3 office hours, 2:30 to 3:30 and 5 to 6. And more information about how to get to those office hours is on Canvas. Good luck on the quiz tonight. Okay, if there are no questions, I'm going to exit the Zoom. Let's see.
Can I ask one quick question?
Yeah, go ahead.
So for number 4 on the practice quiz for quiz 3 here, I assume that you're just like, to answer this question, you're just drawing the arrows from like n=1 or n=2 up to 6, and then back from 6 down to the ground state. Is that what I'm supposed to do here to get the answer?
So let's see. This is the practice quiz?
Yes.
Okay, and it was question 4?
Yes.
Okay, let me just read through it. Yeah, you should draw the energy level diagram and think about what happens when it's in the n=6 state, and then it de-excites. So it can go down to, n=5, 4, 3, 2, and 1.
Mm-hmm.
But once it goes down like that from n=6 to n=5, then from 5, it can go down to any of the other ones below it.
Okay, so it doesn't have to go straight from 5 down to 1 then. Okay.
Right. So you can have lots of different wavelengths coming out because of that.
I see. Okay, thank you. That makes more sense.
Yep.
Thank you.
I have a quick question.
Sure.
Have we ever observed tunneling? And
Yeah, I was just going to answer that in the chat. The short answer is yes. And in fact, it's what's a scanning tunneling, I think that's what it's called, microscope, works based on. And it allows us to image sort of subatomic scale bumps in samples, which can be useful for biological and chemical applications. It's definitely been observed.
interesting.
Yep. I'm not sure when it was first observed, but now it's to the point where it's basically the basis for technology. So, in other words, it's extremely well understood.
And what's like the most significant benefit from understanding that this is possible?
I'm hard pressed to answer what the most significant benefit is, but I mean, just for example, scanning tunneling microscopes are able to image things like, viruses, and they can image very, very small well, I guess that's an electron microscope that I'm referring to. A scanning tunneling microscope can image like the surfaces of materials. So it can be very useful for designing new materials, for example, or trying to understand how materials might interact with the surface of another material.
Okay. So
For example,
let's use it as a tool currently rather than like we use it to our benefit.
yeah. It's definitely a tool. We understand it well enough to be having it in applications as opposed to trying to see, oh, are we actually seeing tunneling here or not? I mean, we know how to make it happen and how to interpret it when it does, and yeah, it's now used as a tool more than anything else.
Awesome. All right, cool. Thank you.
You're welcome. Any other questions? Okay, thanks everybody. Oh, bye-bye.